All right, so chapter 7, lesson 5, graphing systems of inequalities. So we're going to learn how to solve systems of inequalities by graphing. We're going to learn how to solve real-world problems involving systems of inequalities. So some vocabulary to keep in mind is what is a system of inequalities? So we worked with mostly in this chapter with systems of equations. And in the very beginning of this chapter, we talked about how to solve systems of equations by graphing. And that was where the two lines intersected, right? There was a point. Well, in systems of inequalities, if you remember graphing linear inequalities, it was we'd had to graph a line, it was either solid or dashed, and then we had to like either shade on one side of the line or the other. Well, that's going to be this times two, right? So we're going to graph two linear inequalities, and our solutions is not going to be where the two lines overlap, but where the two shaded areas overlap. Okay, and so that's what we're going to examine today. So, how can you use a system of inequalities to plan a sensible diet? So it says Joshua watches what he eats. His doctor told him to eat between 2,000 and 2,400 calories per day. The doctor also wants him to keep his daily fat intake between 60 and 75 grams. And the graph indicates the appropriate amounts of calories and fat for Joshua. The graph is a system of inequalities and he should try to keep his calorie fat intake and amounts represented in the green section. So these two lines represent the amount of fat he should have per day, right? It should be somewhere in this yellow area. And in this blue area represents the amount of calories he should eat per day, right? Well, based off these constraints, Josh should be eating his food somewhere in this overlapping area, which is this green area, where he's in the right amount of daily calories and also in the correct amount of grams of fat per day that he's eating. So this would represent a system of inequalities, and the solution to the system can only be represented graphically because there's an infinite number of points that occupy this shaded area right here, this overlapping shaded area. So that's what we're going to examine today. System of inequalities. To solve a system of inequalities, you need to find the ordered pairs that satisfy all the inequalities involved. One way to do this is to graph the inequalities on the same coordinate plane. The solution set is represented by the intersection or overlap of the graphs. So here's an example. Solve by graphing. Solve the system of inequalities by graphing. We have the inequality y is less than negative x plus 1, and y is less than or equal to 2x plus 3. Luckily, these two inequalities are already in slope-intercept form, right? Y equals mx plus b. So this first one I can tell has a slope of negative 1 and a y-intercept of positive 1. The second inequality has a slope of positive 2 and a y-intercept of positive 3. So if I wanted to graph these, here's my coordinate grid here. I'm going to go ahead and take a look at my two inequalities. So let's look at this first one. Again, it has a y-intercept of positive 1, so that means I'm going to start here. And then it's got a slope of negative 1, so that means I'm going to go down 1, right 1. So it would look like a line like this. And then remember, I have to test to see what side of the line I have to shade. So if I were to test the point 0, 0 in my inequality, it would tell me that 0 has to be less than 1 if I calculate it out. Is 0 less than 1? And the answer is yes. So that means this would be shaded on this side of the line. Then I go ahead and take a look at the second inequality. So I'll do that in green. So again, I'm going to start with my y-intercept of positive 3, which is located right up here. And then I'm going to go ahead and count my slope, which is positive 2. So it's going to go up 2 over 1, up 2 over 1. And it's going to make a solid line. So now the previous line was dashed because it was not equal to the line, right? So none of the points can be on the line. But the second equation, or inequality, is equal to. So that one has a solid line. So again, I'm going to go ahead and test what side of the line I'm going to shade. I'm going to test the point 0, 0 again. So if I plug 0 in for x and y, that's going to tell me that 0 has to be less than or equal to 3, which is true. So that means I am going to shade on this side of the green line. So there's the green shaded area. So remember, my solution to this system, though, is where the two areas overlap. So basically, they overlap in this area right here that I've shaded in red. So any points that are in this red shaded area and on the green line would work as a solution. Anything that's outside of the red shaded area or on the blue line do not work as a solution, right? So this is a graphical representation of the solution to this problem. So any x and y coordinate in the red area counts as a solution or on the green line, right? Obviously not on the green line over here because that wouldn't be part of the area. So again, if I look back at this problem that I was working on, the solution includes the ordered pairs in this green area here and represents the solutions to this problem. So what happens if we were asked to solve a system of inequalities like this, right? So they give us two inequalities. Now you notice these two inequalities are not in slope-intercept form, right? They're not in that y equals mx plus b form. But we can convert them to that form to make them easier to graph. The easiest way to do that is to solve for y, get the y all by itself. So I'm going to start out by adding 2x to both sides, and that's going to give me y is less than 2x plus 2. So now I can see for this inequality, it has a slope of positive 2 and a y-intercept of positive 2. And in this other one, again, I'm going to solve for y, subtract x from both sides, and I get y is greater than or equal to negative x minus 3. So this one has a slope of negative 1 and a y-intercept of negative 3. So now let's go ahead and graph them. So I'm going to graph this one in blue. Again, I'm going to start at the y-intercept of positive 2, and it also has a slope of positive 2, so it's going to go up 2 over 1, up 2 over 1. It is dashed because it cannot equal the line. And then I have to decide what side of the line I shade. So I'm going to test the point 0, 0. If I substitute 0 in for x and y, that's going to tell me that 0 is less than 2. So that is true. So that means I'm going to shade below the line over here. And then now I'm going to go ahead and graph the second inequality, which is I'm going to start at the y-intercept of negative 3, which is down here, and then count my slope, which is negative 1, down 1, right 1, down 1, right 1, which looks like that. That one would be solid. And then when I test the point 0, 0, it does work because 0 would be greater than negative 3. So that means I would shade this side of the line. So now I can see my two shaded areas, and I can see that they overlap over here, which now I've highlighted in red. So basically any x and y coordinate in the red shaded area or on the line count as a solution. So what happens if we encounter something that doesn't quite make sense? So there are times when we can get no solution for a problem. So let's go ahead and solve this system of inequalities by graphing. So if I have the graphs x minus y equals negative 1 and x minus y equals 3, they are parallel to each other because if I look at it, if I were to graph these, right, I would get two lines. I get y equals, if I solve it for y, I get y is less than negative x, or sorry, yeah, y equals x plus 1. And then I would get y equals or greater than x minus 3. And those are two parallel lines. And since those two parallel lines, and then if I were to test them, I would shade on above the line on this one, below the line on this one. And if you notice, if the two shaded areas don't overlap at all, like this area will never overlap this area down here, this would represent an inequality that has no solution, right? The system has no x and y coordinates that is a solution for this problem and for this problem. So therefore, we would encounter a problem that has no solution. Let's look at another example. We're going to use a system of inequalities to solve this problem below. It says the middle 50% of the year students attending Florida State University score between 520 and 620, inclusive. On the verbal portion of the SAT and between 530 and 630 inclusive on the math portion. We're going to graph the scores that a student would need to be in the middle 50% of Florida State University freshmen. So the verbal score has to be between 520 and 620 inclusive, and the math score is between 530 and 630 inclusive. That just means they're included in between those two numbers. So if V equals the verbal score and M equals the math score, the following inequalities represent the middle 50% of Florida State University freshmen. So here's my first inequality. V has to be greater than 520, greater than or equal to, and then less than or equal to 620. And the math score has to be greater than or equal to 530 and less than or equal to 630. So that inclusive means that it can be equal to either one of those numbers. So this is what the graph would look like. Again, here's the math score, right? It's got to be between 630 and 530. And then the verbal score has to be between 520 and 620. So in order for a student to be in the middle 50% of freshmen, they would need to have a verbal and math score in this green shaded area there, because that would satisfy both of these solutions for both of those inequalities. Let's look at one last problem. Let's use a system of inequalities. To ensure the growing season of sufficient length, Mr. Hobson has at most 16 days left to plant his corn and soybean crops. He can plant corn at a rate of 250 acres per day and soybeans at a rate of 200 acres per day. If he has at most 3,500 acres available, how many acres of each type of crop can he plant? So if we let C be equal to the number of days that corn will be planted and S equal the number of days that soybeans will be planted, since both C and S represent number of days, neither can be a negative number. The following system of inequalities can be used to represent the conditions of this problem. So we know that C, the number of days that he plants corn, has to be greater than or equal to 0, right? Because it's got to be positive. Can't be any negative number of days. Same with the number of days for soy. So those are two inequalities that we have. And if I take the number of days of corn plus the number of days of soybean, that has to be less than or equal to 16 because he only has 16 days left to plant. And then 250C plus 200S has to be less than or equal to 3,500 because he has 250 acres per day that he can do for corn and 200 acres per day that can be done for soy. And he has a total of 3,500 acres available. So the solution set is all the ordered pairs. So if you were to graph these two inequalities, they would make these lines with a shaded area below. So the overlapping area is this green one here. So basically, he could do any amount of planting of soy and corn within the shaded area. Obviously, if he wanted to maximize his profit, he would want to do it further out, right? But anything in here would work. So, for example, 7, 8, right? So 7, 8 would work because it falls in the shaded area. He could plant 7-day corn for 7 days and soybeans for 8 days. In this case, he would use 15 days to plant, right? And he would use 1,750 acres of corn and 1,600 acres of soybean. All right. Well, thank you guys for watching. Let me know if you guys have any questions.